Bangalore.
Yeah, thank you very much, Professor Krishnan. I think I missed a lot of interesting sessions this morning, but I'm going to take where exactly the last word of the previous speaker, so you set the stage well. Though I'd have loved to speak on inspection, as I gather with many friends here. As he said, the next generation is additive manufacturing or 3D printing. So in terms of structural integrity, I'm just going to take you into a slightly different realm. Which is like if you have welding, if you have, a lot of people previously spoke about residual life assessment. How do we develop smart testing methods? Well, you're talking of AI and ML and a lot of drones and all that. How do we develop small scale testing? The colleague from TCR also mentioned a lot of things. So I'm going to take you right through that. This is a little bit of research, but it's already undergone technology transfer. And the key here is collaboration. So I come from the gas turbine, both land-based as well as industrial aero engines. And if you look at this, the product life cycle is typically about 10 years. I won't take you through Pratt Whitney's military and commercial engines. And some of you might have flown today in Indigo, Vistara, and hopefully some of you had flights cancelled, and it's always been in the news the last 2-3 weeks or about a month, the Go First and Pratt Whitney litigation. But notwithstanding all that, if you look at this engineering marvel of the geared turbofan, it takes about a decade for this product to come. And in the refineries and, the petrochemical sector, all of you come from, it's a very long cycle product. We want things to last for 25-30 years without breaking down. So how do we develop intelligent test systems? And we're always at loggerheads with ASTM on that because, they're really very picky. Many of you are on committees. Many of you are leading the committees in ASTM. So this is towards that, marching a little bit ahead in additive manufacturing. I did work in the oil and gas sector with additive, but today what I'm going to share is more of academic industry research towards aero engine sector. And it could easily pervade through any of the stuff that you're talking, reformers, boiler tubes, and such like that for residual life assessment. So, in the context of aero engines, we know there are two words, buzzwords, hotter, and lighter. So, if I can put a magnesium-based alloy, entire engine out of it, we'll all be very happy. All of you here will be very happy because you can develop new inspection technologies and so on. But some of the main things with respect to asset management integrity are these 5 things, where it's a low-hanging fruit, additive manufacturing or metal 3D printing in particular. And then we're looking at now large-scale structures. ISRO and NASA, we keep hearing, they keep flying on a very, short term in the sense not lakhs of parts, not hundreds of parts, but very customized, specific to the satellites and so on. Where we are working on is in the last 3 areas, which is new alloy development, repair, where additive is a unique solution provider, of course inspection technologies. I'll touch upon that a little bit, but today I'm going to talk about small scale testing because this conference is, I'd like to thank Dr. Shyam Sundar for actually inviting me to this as part of the symposium, and this is where we've made a mark in a technology transfer. So I'm going to talk of very tiny specimens. How can you take, without damaging the, boiler tube or without damaging a rotor in a turbine, take small parts and be able to look at the structural integrity. I do have a request to make that please don't take photographs because I only have permission to, present it and not, it's not. I'll be very happy to share some of the published work. So in the context of small scale testing, what some of our group has been, we've been partnering with, of course, IISc Bangalore, because our office is right here. We have a center of excellence here at IISc, IIT Hyderabad and IIT Bombay and Roper. And we get some of our samples in a whole bunch of new alloys in metal 3D printing. Because right now what has happened is it's reached an asymptote in terms of, about half a dozen or maybe a dozen alloys that everybody in 3D printing world is taking, starting with the LEAP engine fuel nozzle of the GE fame. So we're looking at hot section components, we're looking at other kind of steels, we're looking at larger rotor alloys, so that accelerated adoption and qualification of 3D printing, metal 3D printing, additive manufacturing, including repair and refurbishment of very difficult, like say cast iron and stuff like that. So we're trying to do that from let's say technology readiness level, about 1 to 1.5 to about 3.5, not yet 4 there, but that's a stage, that's what I'm going to share. And I'd like to highlight this, as I told you, small scale, high throughput testing. So, for example, all of you know, if we have to actually qualify a new process, new manufacturing process, new weldment, whatever, then we need to do a lot of tests, especially if it's a high temperature subjected to creep. Why even a room temperature in titanium alloys, it creeps at room temperature. So we have to do multiple tests at different stresses, different temperatures, and then, especially take a small blade, either a steam turbine or a gas turbine blade. How do I know its structural integrity? If there's no visual in any of the inspection technologies, including some of the videos that he showed, my good friend Shamsundar showed, there's no methodology including micro CT to be able to detect defects at the level at which we have a layer by layer process in additive manufacturing. Yet additive is poised to be truly industry 4.0 because it takes inputs from a CAD model, converts into a G code, and so on and so forth. There's a layer by layer process, and the layer thickness is probably thinner than the strand of one single strand of hair, at least on my head. So what we are trying to do with these new alloys to develop, and partnering this in this case with my colleagues in materials engineering at Indian Institute of Science, we've been doing this for about 7-8 years and have covered about 8-9 alloys, including conventional welding, electron beam welding, TIG welding, as well as for new alloy development accelerated qualifications. So if you look at conventional ASTM, we have 100 millimeter, 4 inches, 2 inches, and so on. In contrast, we are developing an entire specimen which is no more than half an inch, and and the whole thickness of it could be as low as 500 microns, 0.5 millimeters. Take test specimens out of it and prove that the mechanical properties, especially the strength and creep properties, in this particular example it's creep, we're also working on fatigue, of course, is equivalent to the standard ASTM large test specimens, and thereby accelerate. So it's basically a high throughput testing, and the technology involves a completely different paradigm shift to uniaxial tension or compression, and it's via a bending, a cantilever bending. We're all used to 3-point bending, 4-point bending in college, but this is single cantilever bending load. So I'll share you a couple of videos. So this is just to show in our lab that we have test specimens as big as this. He may be well aware we get large test specimens also, but we are talking of very tiny and equivalence in mechanical properties. So as part of the assessing the structural integrity, and where are we using? We're using digital image correlation. I think many of you will be using it. Many of the test labs are now no longer talking of mechanical strain gauges. We're going, of course, in the last 2 decades it's been very, very popular to use digital image correlation. So we're mapping strains. You can see the load being applied here, simple uniaxial tensile, of course at temperature, because it's creep we need to go to high temperature, and we're mapping using a single test specimen. At one particular temperature we get a whole range of stresses. Imagine not having to do multiple experiments, and you're also able to look, especially in the context of location specific properties. Let's say in a rotor, I cannot take a rotor which is functioning and cut it up and weld it back again and put it. Already you're looking at the structural integrity. So we take very tiny specimens, establish in the lab the equivalence, prove with standard ASTM test specimens, and the beauty is the high throughput. So in the context of additive, it's a panacea, because then you're able to get near net shape parts. Somebody talked about thin structures earlier in the session. So you're looking at very thin sections. The heat transfer there is completely different from a bulk ASTM test specimens. It's like night and day, in an additive context, because you don't have a sonic inspection, something for sonic inspection which you're machining away. You do need to inspect the actual, the bottle if it is made as it is. You don't have bulk and angle detectors to be able to fine tune all that. So I'm going to leave you with that thought, but I'm going to continue in a couple of slides to show you. So we do establish, so the top shows you, at least if you can count 1, 2, 3, 4, about 16 tests, the conventional uniaxial creep testing. This is an example of a brand new high strength aluminum alloy for a landing gear application via the laser powder bed fusion techniques. It's called A205, very, very high strength, thermal stability, strengths of about 350 to 400 megapascal at 250 degrees centigrade for about long times. So these are many, many uniaxial creep tests done right here at temperature. This is one single bending creep test which is able to not only give uniaxial tension but also compression. everything in one little bar. If you want, you can repeat it once more, but imagine taking a tiny specimen, it's not more than an inch and 2 millimeters in cross section, you're getting the entire creep curves. And then of course, since I'm an electron microscopist, we can't not look at what is the mechanism of creep. Is it the same, especially in a new alloy development for accelerated, product development in the aero engine sector. And then we're looking at very, very advanced techniques, right here in the institute, atom probe tomography. For example, this is about 2 nanometers, each of these theta prime aluminum copper alloy precipitate, 2 nanometers by 10 nanometers. That is when it is coarsened. So you can imagine today we have, he also said at the beginning, Dr. Krishnan said, everything is there in India. So absolutely strong believer we are the epicenter if we choose to. So we did detect structure property correlations. Was the creep mechanism different? Because it's very important to know when things are going to stay for a long time, especially in a petrochemical industry, then do we want to how do we compare and contrast the microstructural evolution which takes place with time, which with a small test where you're compressing everything and getting all the data in one test by a very clever mechanism of using bending creep as opposed to uniaxial creep. So we did the correlations, and you can see this equivalence is a master plot. I don't know, the red color shows the uniaxial tension, and the blue and the pink are all taken from one test data at one temperature. So you were able to do one test and get multiple data points, and of course there's a microstructural correlation and the mechanism. And it's been a very, very successful collaboration in additive, in wrought, in cast, and towards accelerated development of high temperature materials, especially very, very high temperatures, nickel-based superalloys, cobalt-based alloys, and also look at failures. For example, last year there was a big gear turbofan failure that was in all the papers, Pratt Whitney engine, and we were able to find the root cause of failures in a titanium compressor disc owing to microtexture using this method. So we're able to identify that. Very successful collaboration with a lot of students worked on it currently in our center. And I'll leave you with this last slide because I can't not talk about, if it's okay, this video. Let me just go out of the mode while I'm coming out. I don't know if it'll run here. Yeah. So what we are doing is, I think, what many of you spoke about, but truly in the additive context, if you look at this video, it's like AI, lots and lots of data. When you're having the scanner going and the laser is actually melting layer by layer into a near net shaped part. And I told you the layer thickness is nothing more than 10 to 50 microns. So how do you detect a defect? I told you the micro CTs and stuff are really not able to detect in an additive category because you need to have optics there. You need to have line of sight when you're actually putting the computer tomography, including the 400 kilowatt machine. So you need something more intelligent, but and I'm sure all of you here, stalwarts out here in inspection technology will come up with something which combines physics, magnetism, and mathematics to come up with a new technique to be able to detect in an additive part. But the closest is to use thermal imaging. There are commercially available tools for all this. How we use it for our part is up to each end user's skill set. So what we are working on is, this is for a high-end directionally solidified nickel-based superalloy. We are trying to build it as a directionally solidified, stage 2 of a gas turbine engine, an aviation gas turbine engine. We are trying to detect, from this, which of these by smart optical measurement systems. Of course, again, university partnership, and we are trying to look at the thermal imaging and try to build a database, of course, using Python and codes, and trying. So the top tells you there is a spatter in that particular layer, and there is a process map that we have done in the lab with simple sample coupons, and we relate. And the bottom, you can see there is no problem at all. It's very uniform. And then we develop a process map for this particular geometry, for this particular alloy chemistry, because it's very dependent on the chemistry of the superalloy as well. And then we are also working on a lot on this particular aspect towards industrialization. So I think with that, I do have there are many more photos here which I can't put, but the key is collaborating with academic institutions. And thank you very much for your time.
If I would request the panelists to